So, good morning, good afternoon, good evening, depends on where you are in the world. So, today we are here to see the talk by Professor Robert Wille from Technical University of Munich, Germany, and SCCH in Austria. But before giving the floor to Robert, just some brief announcements. So, some of the next talks. So, we are going to have a talk by Kaushik Roy from Purdue University. I also have scheduled a talk by Elisabetta Moiselo, and we have others that the flyer is not available yet. But you have a large set of talks that we're giving since 2020. So we have more than 150 talks in this YouTube channel, so available for you. And yeah, here is some excuse to come to Latin America. So LASCA, the flagship conference of CASS Society, so the International Conference of CASS in Region 9, as always, end of February, will be this time in Bento Gonçalves, near Porto Alegre, the most traditional wine region in Brazil. And as you know, there is a selection of best papers that are first published in TCAS 2 uh, in the months of the conference. So the papers are in the journal and only the abstract in the proceedings. And then during the conference, there is an extra evaluation of the presentations. And then some papers are invited to submit an extended version, normally by to 11 pages, to the special issue in TCAS 1. So you have till beginning of September to prepare your papers. I hope to see you all in this nice edition, and it's being prepared a nice set of social events to provide the bigger exchange between the participants. And then LASCA 2026 will be in another nice location in Arequipa, Peru, and 2027 in Panama City. So always interesting locations to go. And also next year is being launched the first IEEE Latin conference on Internet of Things, that is IEEE IoT Technical Community flagship conference. So this conference also will run between different countries in Latin America. So international conference, inviting papers from all around the world. And the IoTTC, as you should know, is composed by 12 IEEE societies. One is the Circuits and Systems Society. So this will be end of April, and the deadline to submit papers will be beginning of November. Then SBCCI is the traditional conference in Brazil, also sponsored by IEEE Circuits and Systems Society. So next one is in João Pessoa, in the northeast of Brazil. So the papers were already selected. And then in 2025, it will be in Manaus. So another edition of Chip in the Jungle. So it was done an edition of Chip in the Jungle year 2020, no, 2000. So 25 years after the first edition, we are returning to Manaus. So you have still a lot of time to prepare your papers. I hope to see you all in this icon edition of the conference. And as you know, also the papers are published in IEEE Explore, and also there is a selection of papers that some of them are invited to be published in IEEE Design and Test. So this year, CASS is celebrating 75 years, and then there is a promotion to ones that were never member of CASS. So free membership to CASS, to professionals, students, everybody. And this promotion goes till next month, because in September started the IEEE membership for 2025 now. So you still have about 1 month to use this opportunity. But we are here today to attend the talk by
Terrific. Not sure if that was just on my end, but your mic was a little bit hard to understand in the last minute, but it's fine. So I hope you can hear me loud and clear. Wait.
Yes.
So you can hear me. Perfect. Great. Then thanks a lot for having me, and thanks a lot for this kind introduction. Yeah, as said, I'm Robert. I'm a little bit context. I consider myself I'm a trained computer scientist, and I consider myself an expert in design automation. So I worked in the design automation community for several years, or more than 15 years actually. And I've got socialized by the design automation community. And of course, in the past years, we worked a lot on the topic I want to talk about today on quantum computing. And I personally believe this is an exciting topic, not only because it is an exciting technology, it's a promising technologies. I have to admit there are lots of challenges before we can make this technology solving real problems, but it is still exciting, it's promising. And I also believe, and this is also what I want to accomplish a little bit with this talk here, I think this is a community where a lot of more design automation experts are needed. And maybe with this talk, because I know the audience are design automation experts as well. So with this talk, I'm trying to, to lure you in a little bit into this domain of quantum computing, to show you a little bit what kind of problems we are dealing with in this quantum computing community, and why and how design automation expertise such as yours can help here. And this is a little bit what I try to accomplish in this talk. And in order to do that, I have literally three aspects I want to cover. First, I want to give you a rough introduction into quantum computing. I will keep it abstract. I definitely cannot cover everything. This would alone, I don't know, consume lots of talks, but I will give you a rough idea what quantum computing is all about. Then we'll discuss a little bit the challenges we have in this particular domain, what kind of problems needs to be solved, what kind of methods are needed. And then I will actually do what the title of my talk promises. I will show you a little bit what design automation can do in order to tackle those problems. And I will try to address the question stated here. Do we have to reinvent the wheel for this new emerging technologies? That means, do we have to start over developing design automation methods for quantum computing from scratch? Or can we maybe use one or two things from the design automation community, which we have learned in the past decades, designing classical conventional circuits and systems? Can we reuse that for quantum computing as well? So those are the kind of three messages I want to convey. And as I said, let's get started by a brief introduction into the basic concepts of quantum computing in general. And I'm doing that by starting with conventional computers and systems today. So trying to, build a bridge how we came from classical computings like these notebooks, or as you know, classical computers are used everywhere these days. We have chips, electronic circuits and systems in cars and trains and washing machines. Of course, all the AI solutions which are around these days rely on electronic systems, certain systems. So this is the basis. And of course, this was possible because of the design automation community and their contributions in the past decades. And what I still find fascinating about this technology is, despite the vast majority of applications and the broadness and the ubiquity where those technologies are applied today, still this technology boils down to 0 and 1. And I'm still teaching, first semester classes on computer architecture and digital circuits. And I still find it fascinating to explain how simple this actually is, that you can, just realize an AND gate and an XOR gate, and then you have a half adder. And then if you want to have a full adder, you just apply a couple of more gates and OR gates and stuff like that. And then in order to do addition, you just do a little bit more of that. So computers, the main principles of electric systems and circuits are relatively simple. But of course, if you combine them in order to get complex processes, you get a complex system for which you need design automation. And this is the technology itself, which evolved over the past decades. And the technology itself still is really powerful, right? So you could argue, why do we need a quantum computer? The technology we have so far based on electrical circuits is rather powerful. And just to sketch that, you all know that, but just to sketch that a little bit, because this technology allows you to represent all kinds of problems on data with 0 and 1 only. So if you have two inputs, then you can encode 4 possible states, which you can encode. With 3 inputs, you encode 8 states, and you know how this kind of works. With every bit you get more, you double the amount of states, amount of outputs you can generate. So if you have 300 inputs as an example, then you can generate functions which can generate 2 to the power of 300 possible outputs, or you can basically encode 2 to the power of 300 possible cases, which translates to something like 10 to the power of 90 possible cases. So, and this is also one of those aspects what I find so fascinating about this technology, because everything boils down to zeros and ones, and the main concepts, as I said, and half adder and things like that are relatively simple. But if you plug lots of these components together, you end up suddenly with a complexity that a circuit with 300 inputs can generate 10 to the power of 90 possible cases. And just to put that into perspective, physicists somehow came out with the fact that the number of atoms in the universe is approximately 10 to the power of 78. So it is easier to count the number of the atoms in the universe rather than enumerating all possible outputs of a circuit composed of 300 inputs. So why I'm bringing that up, why I'm showing you that, is the following: that conventional circuits and systems are relatively very complex and powerful. In general, if I have a problem, a search problem, for example, I still can encode this problem with a conventional machine. So the problem is not that conventional machines kind of provided with a limit on what kind of problems I technically can represent or can at least try to solve with a conventional computer. The main problem is just that even if I have my problem, let's assume I have a search problem, and out of 2 to the power of 300 cases, I want to search a minimal solution of some sort of problem. So the problem is not that I cannot represent that somehow. The problem is that if I have a task like that, in the worst case, I have to enumeratively go through all possible cases in order to find my minimal solution. So the problem we have is often a complexity problem, in the sense that sort of like, going through 2 to the power of 300 or 10 to the power of 90 cases, this is the time-consuming thing. Or if we represent it with memory, then we have a memory problem. So the main problem is, the main issue is I can represent my problem using conventional systems, but then I may have to run this computer to go through all possibilities for hundreds of years, and this limits today's computers when I want to solve certain problems. And as you know, we have, particularly in design automation, we have a lot of problems which technically can be formulated, and we can write in very simple script and then start a computer, but it will take centuries until we get a corresponding solution. And this is sort of like the main problem. And of course, we can come up with better heuristics, we can come up with tuning strategies, but the complexity remains. So even if I don't enumerate all possible solutions, but I use clever search algorithms and techniques, even then I'm running into certain problems. And now the issue is in quantum computing, and now I'm abstracting a lot, and physicists would kill me for this way of abstraction, but just to provide you with an intuition what a quantum computer does in a very simplistic and not very much accurate way, but as an intuition, what a quantum computer does is it allows you to not only apply a 0 or a 1 for every input, but it allows you to apply 0 and 1 at the same time. This is called superposition. There are a couple of other quantum mechanical effects which can be exploited, such as entanglement and a couple of further things. And those concepts allow for a massive parallelism, and it kind of allows to tackle a problem or to solve a problem while running or to process a problem while running all possible inputs at the same time. And this, again, very abstractly spoken, very intuitively and not perfectly accurately spoken, this gives you sort of like, if you do this in this fashion, this gives you at the output all possible results at the same time. What I'm trying to say is, if you have your problem with 2 to the power of 300 possibilities, very abstractly spoken, you can run all possible inputs at the same time, and then you get all possible results at the same time. So you literally get an output state which kind of encoded in a quantum mechanical fashion has all your solutions stored somehow in this state at the same time. So this is what a quantum computer does, again, in an abstract fashion. The problem, the caveat, however, is that you cannot completely measure this resulting quantum state. So the quantum state kind of includes the desired results, But, and this is the problem, why it doesn't work out that beautifully, otherwise it would be a game changer. The problem is the moment you measure this state, that means the moment you check out, you want to read out your state, you don't get, you know, the detailed information about the quantum state, but what you do is you get one of the possible basic states. That means one of the possible results, one of the possible solutions with a certain probability. It means if you just have that, what you get is you kind of put your inputs in superposition, zeros and one at the same time. You get all possible results kind of encoded into the quantum state, but if you measure this state, you just get one of the possible output combinations with a certain probability. So this doesn't bring any help very much, but now what you can still do is, since the original state kind of have your solution encoded, what you can do in addition to that, once you have the state, you can apply what I'm calling here tricks. So you can apply for some applications, or actually for many applications, not for all, but for several of them, you can apply certain tricks. That means you can apply further operations on your resulting state, which increase the probability of your desired result and decreases the probability of the results you're not interested in. So in other words, if you have an optimization problem, what you can do is you can encode your optimization problem as some sort of a quantum algorithm or quantum circuit. Then you apply zeros and one at the same time as the input. You run your quantum circuit. By that, you compute all possible results at the same time, including the desired result. That means the minimum of your optimization problem, for example. And then you apply these tricks, something which we call amplitude amplification. And then by the application of these tricks, you increase the probability of your desired result. And then you still have a probabilistic result. That means when you measure the resulting state, you still get with a certain probability one of the possible output assignments. But due to this amplitude amplification, you get the desired result with a higher probability. And that overall now allows for lots of applications in the future. And this is what motivated, you know, the who's who in the IT industry, IBM, Google, Microsoft, you name it, lots of startup, an entire industry, but even a bigger community started working on exploiting and utilizing these effects. And there are some granted long-term applications. The most famous one, you probably have heard about that, is cryptography, integer factorization. And this is definitely a long-term thing. We are by far not there yet, but conceptually, theoretically, it has been proven that you can you can solve integer factorization much, much faster than with classical computers. And if we can scale that accordingly, this would actually break, I don't know, internet cryptography, for example. But this is more long-term application. There are further applications in nature, in simulation of, I don't know, climate change, for example. I mentioned optimization problems already. With exactly this idea I tried to sketch, you have an optimization problem, you have all solutions of your optimization problem, and then you increase the probability of measuring your desired, your minimal solutions for your optimization problem. Those are applications which are very famous in finance, the applications, machine learning, and so on and so forth. So roughly, this is the concept of quantum computing and why quantum computing is so interesting. And again, in a very abstract fashion, but I hope it gives you some sort of a rough idea what all this is about. And this is a development which has been done for decades. The first ideas of quantum computing have been done in the last century. For example, this factorization result, the theoretical result, was done in the 90s of the last century. So there was the first proof. But quantum computing for a long time still remained dreams of the future because the technology wasn't there yet. We had those concepts, but we had no means to physically implement that. And then in the 2000 years, first implementation came around and so on and so forth. What really gave this entire community a lot of momentum was a couple of years back, 2017, so 7 years back now or so, IBM made their first quantum computer publicly available. Google followed suit. Now AWS are providing a lot of machines, startups like AQT, IQM, a couple of others providing quantum computers. And they are not there yet that they're arbitrarily scalable. But what is interesting is if you look at the corresponding roadmaps of those companies. For example, this is a roadmap from IBM with planning in the next years. It's a little bit older one, but even then for 2026, they're planning for tens of thousands or hundreds of thousands of qubits. Then you have Rigetti, where they're also talking about thousands of qubits. Or this is a chart from IonQ. Also, you can see a little bit the growth of the qubits. What is important, though, of course, those are roadmaps and maybe even some sort of like plans of those companies. Of course, you always should take that with a grain of salt. A very important part of that is also that just the number of qubits, it's one indication of how powerful a quantum computer is, but should also be taken with a grain of salt, because you can have millions of qubits, but the huge problem with the technology is noise and the quality, the fidelity of those qubits. So you can have easily lots of qubits, but they have literally less. They have lots of noise, less fidelity. So you could have thousands of qubits, but you cannot do anything useful for that. So it's a little bit more complicated than boiling it down to qubits. But what this roadmap shows and what these charts show is a little bit like there's a lot of momentum going on, lots of progress. New technologies are being investigated, more physicists, experimentalists making qubits more stable, less prone to errors. Still lots of challenges in there, and once in a while you ask yourself, are we really getting into practical relevant solutions? But there is a lot of activities and a lot of momentum. And what I find interesting as a design automation expert is there's a huge analogy to the development of conventional computers. So nowadays, this is a picture of, I'm pretty sure this is an IBM quantum computer. So this is a quantum computer from IBM. And so this is sort of like, looks very similar to, the original computers we have in classical circuits and systems, right? So also in our design automation community, we had sort of like we started with small scale computers, and that is maybe where we are in quantum computing today. And then in classical computing, we had this Moore's law, and this tremendous improvement, which eventually led to this digital revolution. And again, there are lots of physical challenges in there. We have lots of problems to solve, but maybe in quantum computing, we see in several similar development, but also quantum computers getting better and better. And I'm not saying that we're going to have a second Moore's law for quantum computing, but if the momentum keeps going, we're definitely going to have more scalable, and then that's more important, more fault tolerant, more less error prone systems. And if we have that, then we have to think about how we probably use them. And in the conventional realm, in conventional circuits and systems, we had all those accomplishments, which was of course a great accomplishment by electrical engineers working on that domain. But design automation, electronic design automation, and software for design automation also enabled their success, because originally there's no problem, as I stated before, there's no problem to design a half adder and a full adder, and maybe even a 32-bit adder, things like that. But once you design a complex CPU, or once you want to design a graphic card, or an AI core, an AI processor, stuff like that, things get complicated, and you need design automation tools. And our community over the past decades have developed these tools, and they nowadays can handle problems and design tasks of enormous complexity. And for this purpose, we used reasoning engines such as SAT solvers or ILP solvers. We use data structures such as decision diagrams. Lots of technologies, methods have been developed by the design automation community in the past. And we combined all that into very powerful design and compilation flows. So if today the next smartphone is developed, or as said, the next AI application, we have a lot of powerful tools, but also a very integrated design flow. And still, huge teams, like the next smartphone is developed by a lot of teams who do a specification, who do an initial prototypical implementation, who then synthesize and compile, who test, who verify, and so on and so forth. So there is an entire industry and an entire ecosystem emerged on the design of electronic circuits and systems. And if you now look on quantum computer, if you look how is the situation there, we also have software tools there, and we also have some initial design flows there. But I wouldn't say that, I would say that the software for quantum computing is not as powerful as the software we take for granted in design automation. And the same also for the flows. We have initial flows, but we still don't know what is the perfect design flow. How do we handle, how do we, sort of like properly encode an application in a fashion which is suitable for a quantum computer? What is the best way of compiling a quantum computer? So we're still developing those corresponding compilation flows. There has been a lot of progress in the past year as well, but again, compared to what we take for granted in the conventional circuit and system design, we are still in the infancy. And this is, in my opinion, a problem because right now, still too few people from our community, from our design automation community, develop these tools or develop those flows because they're just not in quantum computing yet. And this is something what I said want to change, because if you don't get design automation, or let me put this other way, if you don't get more design automation expertise into the domain of quantum computing, we may end up in a situation where we have those machines, where these machines suddenly scale perfectly and suddenly work for practical relevant applications, but then we don't have any methods to use or design them. So there is a risk that we're running into a design gap where the machines are there, but not the software tools we need, and nor the flows we want to have. So this is my motivation a little bit, why we need design automation expertise in this domain. So, and of course, again, all in an effort to lure you in a little bit in this community. So let's talk about what that now means. So if I want to lure you in, I want to do that because I want our community to solve certain challenges, to use our expertise to solve certain problems. So let's talk a little bit, again, in an abstract view, what kind of challenges are there in order to do that. And first, and I started with some not the most important challenges, but just to get you easing in a little bit in a different paradigm, the entire programming is differently. You're not talking anymore about an adder, how to realize an adder and things like that. Well, you still have addition and quantum computing, but you have to think a little bit differently. And the biggest, one of the biggest paradigms is that in quantum computing, every operation inherently is reversible. Just to illustrate that a little bit, consider this multiplication, A times B. If A is 4 and B is 5, obviously, if you compute from the inputs to the outputs, the product is 20, everything is fine, right? But what happens if you want to do it the other way around? If you want to, if I give you 20 and I tell you, and I ask you, can you please do the inverse? That is what makes a computation reversible, that you can not only compute from the inputs to the outputs, but also from the outputs to the inputs. So if you have that, and I give you 20 as a product, what would be the output? What would be the input, of course? It could be 4 and 5 again, but it could also be 2 and 10, right? So just the multiplication, as we typically take for granted, is not reversible, and by that is not allowed to be applied in a quantum computer. It's a different paradigm. We can easily resolve that by just, rather than using just A times B, or by using, assignment operations like, I don't know, C is assigned to A times B. We're using reversible assignment operation as shown here. Something like that. You take this A times B and then you add it to a third value. You not assign it directly, but you do a reversible assignment like that. Because if you do something like that and A is 4, B is 5, and C is 0, you can compute from the inputs to the output. You get the result C is 20. But if I give you only the output, you see this assignment is this is the increase assignment. The inverse of that is the decrease assignment. So if I give you these 3 outputs, you still can determine those inputs here. So this is the thing in order to what you have to consider when you do quantum computing. It's a different paradigm, but it is, to be honest, it's not even the big deal breaker here. Just as an example to ease you in, this is a little bit a different paradigm you have to consider. It's doable, works out, but it's different, and you cannot directly write C++ code in order to define a quantum circuit or a quantum algorithm. Even more problematic and even more challenging is the real quantum computing characteristics. Most importantly, I mentioned that before, that you not only have zeros and ones, but you also have 0 and 1 at the same time. That means you have superposition. This is where things get challenging. You suddenly have to think about how to encode and how your algorithm deals with certain states where you not only have zeros and ones, but also superposition, entanglements, a lot of effects which are not really intuitive and kind of hard to explain, but after a while you get the grip on it. Also something like that, you of course then suddenly have to understand quantum operations. I think this is also a big challenge paradigm-wise, because just think about it, when we talk about a half adder or a full adder in conventional computing, everyone, I said before, I do classes, first semester classes, where I describe a half adder, a full adder, and how a processor works like that. What is easy here is I already can assume that everyone in the room knows what addition is, what multiplication is, right? The operations the electrical circuit and system should realize all are kind of common knowledge and is aware there. I assume nobody who has never worked in quantum computing before knows what a Hadamard operation is, what a phase shift operation is. So a problem is, in order to get involved in quantum computing, you also need an understanding of quantum operations. Not a big deal. It's so like we have abstractions, we have models. It's not that you have to study quantum physics for that, but you cannot just rely on everyone knows how addition works, how multiplication works. You have to learn certain operations. Then, excuse me, then there are of course lots of physical constraints. I already indicated a little bit before, every quantum operation is prone to errors. There is a lot of noise going on, so error correction is going to be a huge challenge. We can, I don't get into much detail, but just a small bullet error correcting is a vastly complicated problem where we hardly scratched the surface yet, and which still will give us a lot of headaches in the upcoming years. It's something we have to deal with, and a couple of other things as well. So just from the paradigms, from the concepts, this is what we have to tackle when it comes to quantum computing. On top of that, quantum computing also from the kind of design tasks we have poses substantially more challenging threats to us. Let me give you an example with simulation. In classical circuit systems, simulation is kind of straightforward, at least logic simulation. For example, if I have a circuit like that, and if I have an input assignment, simulation is really easy. I just traverse my circuit. I touch every gate. For every gate, I check out what is the input signal of this gate. And then for this NOT gate here, if the input is 0, then I can determine the output, which is 1. I can do the same for this inverter here. I can do the same for this AND gate here, and for this AND gate, and for this OR gate. And then I'm done with my simulation. In conventional circuits, simulation is a linear problem, linear with respect to the number of gates. Now in quantum computing, the problem gets much more complicated because, as said before, in quantum computing, in signal or in single qubit, so that's what we call a bit in the quantum realm, a qubit can not only be 0 or 1, but it can be 0 and 1 at the same time. And because of that, an input state, for example, has to describe that somehow. That means we need a description like this one, which kind of, this is what these alpha variables do, which kind of represents, we call these alphas amplitudes, and naively spoken, abstractly spoken, they kind of represent the probability in which this state falls back to 0, 0, 0, 1, 1, 0, and 1, 1. That means because these two qubits here can be 0 and 1 at the same time, I need to somehow describe the amplitudes for all possible basis states. And this means that just a single quantum state requires an exponentially large description. Because if I have 2 qubits, I require 2 to the power of 2 of those amplitudes. If I have 3 qubits, this vector needs to be of size 2 to the power of 3, that means 8. And that means if I want to simulate an, 50 qubit circuit, I need to describe the input state by a 2 to the power of 50, by a vector of the size 2 to the power of 50. So I have an exponential complexity in just describing a single qubit state compared to the linear complexity here. And that means all the simple tasks, such as a logic simulation, become substantially harder for quantum computing than for conventional circuit systems. So, so this is another challenge which we have to tackle. And then there are further obstacles. Quantum computing still is a highly interdisciplinary field. There are lots of terminologies and formalizations which haven't been figured out yet, different notations, or lots of further challenges. But this is kind of what people who want to get involved in quantum computing have to prepare themselves for. And on the one hand side, this may look a little bit scary. On the other hand, it is also, if you allow me to say that, it is also some sort of a cool playground, because, I mean, just think about this exponential complexity problem here. Of course, on the first glance, this is annoying that suddenly simulation is so complex, but if we really think about what we're doing as design automation experts, we are solving exponentially hard problems all the time, and that's exactly why I think we should be the ones who tackle those tasks as well. And this now brings me to the third part of my talk. How can design automation for quantum computing help? And also, how can people like people who work in design automation in the design automation community but haven't worked on quantum computing yet, how can we make them? How can we sort of like make them enter the community? Because a big feedback or a big problem that I often got from my peers is, hey, I would love to contribute to quantum computing, but I don't understand quantum computing and I don't want to study quantum physics first. And here's the deal, you don't have to. I honestly believe you can do quantum computing research with your design automation background by utilizing models, which we have. A good example is, I'm a computer scientist by training, so I'm not really good in electrical engineering. I know that things like voltages and currents and electrical resistances exist, but I love to work in abstractions. I rather work with, AND gates and OR gates and with zeros and ones and with higher levels of abstractions. And this is where I utilize my expertise and where I make contributions. And now I'm trying to provide you with some very similar things for quantum computing as well. Because I mentioned in quantum computing, I mentioned entanglement, superposition, quantum operations, which are hard, which are not intuitive. So yes, there is a lot of stuff going on in quantum computing, which might be not that intuitive and familiar for a design automation expert, for an engineer, for a computer scientist. But you can boil it down to certain models. And I just want to give you one example for that. For example, I already mentioned that before, a quantum state can be represented by a vector like that. So a state over n qubits can be represented by a state vector of the size 2 to the power of n. In the same fashion, we can describe our operations. The Hadamard operation I mentioned before, the phase shift operation I mentioned before, all quantum operations, every quantum operations can be represented by matrices like that. And here, similarly, these matrices for an n qubit system have a complexity or a size of 2 to the power of n times 2 to the power of n. But they describe the operation. And now what I'm trying to do is sort of like, when you have a state representing, for example, your input state of your quantum system as a vector, and then you have a matrix representing an operation which should be executed on that quantum state, then and you have to describe in this fashion, then you can already make a contribution from a design automation perspective, because you could only with these two, with this vector and with this matrix, you could do quantum circuit simulation. What is that? You have your input state, you have the operation, and in order to simulate what happens if you apply this operation on that input state, all you have to do is you have to do a matrix vector multiplication between this matrix and this vector. So if you solve that, you get the corresponding output state. And here now comes my message a little bit. If you want to make a contribution, but you're afraid that you have to understand quantum computing for that, you could skip a lot of quantum computing details, because the actual problem, the actual challenge which we need to solve here is not understanding this operation. If you have been given this operation in terms of a matrix, you can just accept, okay, this is an operation as a matrix. I may not understand the details of it, but I understand that I have an operation. I understand that I have a state. Both are represented by a matrix and a vector respectively. And I have a matrix vector multiplication problem of exponentially large matrices and vectors. And that is the problem I need to solve. And for that, solving an exponentially hard problem this is where your design automation expertise come in, and where you not necessarily need quantum computing background. Don't get me wrong, at some point it helps to get the quantum background, but in order to get started, the bigger fish to catch here is solving this thing rather than understanding what this matrix stands for. This matrix can be provided to you by the quantum community. Your expertise is needed to solve this exponential problem. This is the message I want to do here. And in a similar fashion, we can now do this for many other design problems. For example, for compilation or synthesis. Again, you may have a matrix like that. This describes an operation or an application which you want to realize. And realizing means you want to represent that in terms of a particular quantum circuit. And quantum circuits look like that. They're a sequence of several operations. You can see these H's here. Those are the Hadamard operations I mentioned before. The other symbols represent other quantum operations. So what you want to do is you want to decompose your overall matrix into a sequence of operations, which by themselves are represented by matrices as well. And then this is what you want to do, because you want to, for example, this operation here at the beginning might not be executable by elementary quantum operations. So you may want to decompose that into elementary operation. As an example, just sketching the idea, this gate here, for example, is usually, depends on the technology. In the meantime, we have technology which elementary supports this gate, but other quantum computers don't support that gate. And then you just have to map that down into a sequence of operations which does the same functionality, but with elementary gates. It's the same thing in the software realm when we compile high-level code into assembly code, or it's the same thing in logic synthesis when we compile, I don't know, an 32-bit adder into a sequence of NAND gates, because this is our technology, right? And then we have a couple of further constraints. I don't want to go into detail, but you have typical steps that, I don't know, for some reasons, these two qubits cannot interact with each other. So you have swap gates, couple of things, or you identify that suddenly, I don't know, two Hadamard gates cancel each other out, so you can remove them, or these gates can be optimized. And what I'm trying to sketch here is that we have a lot of problems here where you literally do what we've done in the design automation community. You have a model, that means these matrices, which represents the overall functionality, but also single gates. And then you have design tasks like decomposition or compilation and synthesis, transforming the high-level matrix into a sequence of elementary matrices, or to do optimization like that. And the interesting thing is, all those problems are most likely NP-hard, exponentially hard problems. Some of them have even proven to be NP-hard. That means many of those problems are exactly in the same complexity class as the typical synthesis and compilation problem. And again, who would be better in solving these kind of problems than our community, right? So like this is one of the messages I want to convey. And then last example, because it's also so nice, verification. If you, for example, have compiled this quantum algorithm into this elementary quantum algorithm, maybe you want to still know whether or not they do both realize the same functionality. And again, this is something in classical design automation problem. We have done equivalence checking for decades in the corresponding realm. And here we have the same problem. One very naive solution could be I translate this circuit back into a matrix, which describes this entire functionality. And then I just have to compare these two matrices, and then I have solved the problem. And the challenge is not that you have to understand quantum computing or quantum physics for that. The challenge is that now you have to ask yourself, how do I compare two matrices which both have an exponential complexity? How can I do this in the most efficient fashion? And that's exactly what we design automation experts can do. So to wrap it down, the basis from a design automation perspective for software for quantum computing are actually vectors and matrices. There's lots of more, and it's a simplified view, but with matrices and vectors, once you handle those, you can do circuit simulation, you can do compilation or synthesis, you can do verification, you can do a lot of things. And the naive way, and the first glance, is you represent them with one or two-dimensional arrays, then you end up in this exponential complexity. And now the question is, can we do better than that? And this literally now is a question for us, for the design automation community, and we have done a couple of things in this regard. We have developed decision diagrams, tensor networks, came from another community, but still is a very powerful thing. Same with the X calculus. There are solutions available who tackle complexity like that. And this is kind of my kind of goal, by going through those models, getting involved, and then utilizing the design automation expertise to tackle problems like that. And I promise I don't want to go too much into details, but one small detail, just to give you a little bit of glimpse how this can work in a little bit more detail. Let me give you one example, exactly how we can solve the problems I sketched before. In particular, how can I represent an exponentially large matrix like this one in a more efficient fashion. And just 5 minutes, a little bit more deep dive, just to give you a little bit of an idea how it can look in detail. And one possible solution, I mentioned it before, is that we can represent that in a decision diagram. That's a data structure which is commonly used in the conventional realm and which can be applied for quantum computing and for representing this matrix in a more efficient fashion as well. Whole idea, as with every decision diagram, I try to decompose my overall matrix or my overall description into sub-descriptions, in this case into sub-matrices. So what I'm trying to do is following. I have one root node with 4 successors, and every successor represents one of the 4 sub-matrices. So this successor here is literally this matrix, sub-matrix. This successor here is this sub-matrix, and so on. With this, I haven't gained anything, but what you can see is what this allows me is, if I now check out these 2 sub-matrices, I can see that those are identical, right? And then that's what decision diagrams do. They decompose, and then identical sub-functions or sub-functionalities, they are shared. So I can literally point to the same data point, and then I save 25% of my memory already. And this is one of the main ideas of the decision diagrams. But I can do more, because if you look at this matrix, you can see the entries of those matrix, they look very, very similar. They actually all have the same subfactor, namely 1 by 2. So what I can do is I can multiply out the subfactor and put the subfactor on the edge. And then what I have is, when I now follow this edge, and this edge has a subfactor as an edge weight, I know whatever follows here, I have to multiply that with 1 by 2, and then I still get my desired values here, but I have kind of normalized my submatrix here. And this doesn't help here a lot, but just check out this submatrix here. Here I can do the same. All the entries here are similar except for a common subfactor. In this case, -1. I could multiply -1 out. And if I do that, I suddenly made these 2 submatrices identical again, and then I can merge. And then I save another 25% of my memory, and I still get all the information, because if I follow this edge which has no edge weight, I only take the original matrix. If I follow this edge with the edge weights -1, I know that I have to multiply this -1 to this submatrix as well. And this is how I can represent this matrix in a more efficient fashion. And if I do this now in a recursive fashion, now I split this submatrix up into further submatrices, the same with here. I can do this in a very similar fashion, in a recursive fashion, for all the other submatrices, and then I end up with a circuit like that, which, utilizing this thing, still describes everything I have in here in this original matrix, but if it works out beautifully, in a more compact fashion. And for many cases, not for all of them, it allows for a more compact representation. And again, this is exactly what we're doing in the conventional circuit and systems realm, and where design automation expertise is used. So this sort of is roughly the idea. I hope I was able to convince you a little bit, or to give you an idea about what is quantum computing, what are the challenges, and why many of those challenges actually can perfectly be addressed by design automation experts. So in order to end my talk, let me summarize that a little bit, and also let me use this as an opportunity for some shameless plugs. As said, we are working on that for quite a while with a fantastic team here at the Technical University of Munich. And as I said, it's our mission to get more experts from design automation into that. And the best way is, of course, talks like that. In this regard, thanks a lot for having me here again. But of course, it is also great to make the methods which we already have publicly available. And that's what we did. All the solutions, the methods we developed in the past for quantum computing using design automation experts. The decision diagram I just showed you, many of those compilers and stuff like that, we implemented all that and we made that publicly available in form of this Munich Quantum Toolkit, which you can see here, which provides a nice collection of lots of solutions which has been developed with a particular design automation background in mind. So for example, it includes a couple of solutions which allow you to encode your application into a quantum circuit. Literally the simulation task I showcased. We have a lot of solutions for that based on decision diagrams, based on other data structures. Compilation I mentioned, I have a couple of compilation methods in there. Verification was mentioned. Error correcting, as said, it's a huge topic. We barely scratched the surface on that. We have some initial solutions, but if you want to get involved in that, lots of way to do there. And of course, also the hardware, the quantum computing hardware needs to be designed at some point. And also here, lots of design automation problem occur, where our expertise can be utilized. And this is what is provided in this Munich Quantum Toolkit. Depends a little bit. Some of those repositories are better documented than others, but we really try a lot. We do continuous integration. We do documentation. It might not be super duper perfect, but it hopefully gives you a good entry point. If you want to get involved, that is the tool you want to use for those design tasks. Of course, important for all those design tasks, they rely on efficient data structures and core methods. Decision diagrams, reasoning engines, all what the design automation community can offer. Also, this is kind of sort of like considered here. And whenever we have a solution which utilizes particular design automation method, we try to incorporate that as well. So this is the first shameless plug. There's another shameless plug because there's also so like in the past years, there's a lot of stuff happening. Lots of progress, and it also showcased that this increased significantly the interest in quantum computing software in general. And for that, a shameless plug, last year we had what we call the Munich Quantum Software Forum. We had the who's who of the software developments for this community in Munich, and we had more than 200 people around. And we're trying to do this this year again on October. Here you can see it on October 24, 25. We're having the software forum again. People from IBM, Intel, NVIDIA, BMW, Classic, IQM, AQT, a couple of more will be there giving keynotes, but also many, many other software developers. So if you're interested in this field, consider participating. On this webpage, you find all the information. You'll find also, if you like, a summary video of last year's event, which also gives you a glimpse. It's a 5-minute video, really worth checking it out, because it gives you a glimpse of the community who's currently built, who's currently growing on this particular thing. So those are my shameless plug. Let me wrap it up. What was the message I wanted to convey? First, quantum computing is an exciting technology. It works substantially different than conventional circuit systems. But as you also can see, is once you have the right models, it's still you can still work with it, even if you're not a quantum physicist. So this is the first big message. I still believe, and I hope this went through as well, is that you need. That this community needs design automation expertise. So more people like us should get involved. And I hope this talk made a small contribution to that. To this end, what I would like to propose here is connect to other communities. We should discuss together how we define models and representations, so that you don't have to become a quantum physicist in order to make a contribution. That is possible. And once you have done that, then disseminate those formalizations, those models, those tools. That's exactly what we try with this Munich Quantum Toolkit, that we're trying to provide what we learned and what we managed in this in our work, that we try to disseminate that to the design automation community, to make it easier for you to get involved. And with this, I would like to thank Ricardo again for this kind introduction, for giving me the opportunity to speak here. And I'm really thankful for that. Thank you very much for your time. If there are questions, of course, I'm happy to answer that. And if you're interested in more, check out the course learning web pages, connect on LinkedIn, or drop me an email. Thank you very much.
Thank you, Robert. So to the attendees, if you have any question, please do it as soon as possible. So I have one question here by Luis Duarte from UFRGS, who said that it's needed more new ideas in quantum computing design, but it's a very complex area. How long does it take for a student to learn and be able to start working in this area?
That's a really good question. It's also sort of like I get that a lot. And of course, a big problem often is that people think they have to study the entire field before they can make a contribution. Point is, of course, you have to have a rough overview. I try to build some bridges by, providing, if you know what a matrix is and what a vector is, you just have to tackle matrix vector multiplication. My recommendation here is hook up maybe with some colleagues, but if you're not in quantum computing yet, then try to get a rough understanding about a particular field. Try to identify, well, is this a nice combinatorial problem where your background may fit, and then try to learn what you need in order to solve the problem, and try to abstract away all the surroundings to make it precise. When I started as a PhD student in this field, I made contributions on some niche areas where I could make a contribution, which I understood. And then it still took me, I don't know, a couple of years until I understood quantum computing better, but I still was able to make contributions because I was focusing on one aspect. And last comment on that, quantum computing is so complex. I often take it with Feynman, who said that if you think you understood quantum computing, you haven't understood it, because it's so unintuitive that even experts like me who are working in the field for years now, for more than 15 years, even I don't think I understood everything. And that's maybe the most important part. It doesn't mean you don't need anything on information. You need some sort of basis, but try to identify a subset you feel comfortable with, and then try to make a contribution there.
Thank you. I see no more questions in the chat. So I have one. Do you have some data about some comparison about power consumption between a solution constructed in a traditional way or using quantum circuits?
That's a very good question. And there's also usually one of those questions I try to dodge because it's really hard to answer, and it depends a lot on the technology. A good example, we have some quantum computing technologies which operate on close to absolute zero, so 0 Kelvin, so on cryogenic temperatures. And here just the power consumption to get too close to 0 Kelvin is immense. And then you have other machines who can work on room temperature. The point is that these machines are not really comparable yet. That's also one of the biggest challenges we have. Everyone is looking for the killer application or for the quantum advantage. So comparing a conventional computer with a quantum computer is really, really hard because they are so different. And today's quantum computers are simply not there yet. And boiling it even down to power consumption is an issue. It's hard to answer. Power consumption, these machines are not trivial yet. We are handling, we're handling quantum physical elements here. So it's really not that simple. And all the prototypical machines we have these days probably have a much bigger power consumption than my smartphone here. But it depends a little bit how this technology will develop. And it will also depend a little bit whether or not a quantum computer will then still allow us to solve some problems more efficiently, because it makes a difference also in power consumption if I solve a problem in a day compared to solving a problem in 300 years. And this is what still has to be investigated. We're definitely not, we the experimentalists are definitely not there yet. And then because of that, it's really hard to make comparisons like that.
So there is a question here by Albuquerque de Gabriel. I think he rewrite several times the same question. The final one is, what do you think is the best way to monetize quantum computing as a student?
I have to be a little bit careful what I'm saying publicly here. So like, let me put it this way. There is at the moment, I said, a lot of momentum going on. And that means a lot of industries and companies are interested, but also public funding agencies are supporting the technology a lot because it has a lot of promises. So that being said, there's a lot of money and funding in the system. And if you have a great idea which could solve one of those challenges, not only the challenges I talked about today, but also the physical challenges. If you have a great idea, you probably, it is not that hard to find support and funding for that. The question will be like how to form a business model out of that. I'm a scientist. I don't know exactly. It depends also a lot. Again, we don't have the killer application yet. If we have in a couple of years, or even in more years, if someone has a killer application, of course, this could easily be monetized. For today, if you have a cool solution to overcome one of those challenges, and you find someone or you hook up with one of those, industries or even, research groups who are trying to solve those challenges, you maybe can only get, monetizing that already right now. As I said, lots of startups are currently funded these days, which build quantum computers and which sell access to quantum computers already. So right now, you also have to be careful. There are also some sort of like bullshit players around. But so like, if you have a cool idea which solves a big problem in this domain, I'm pretty sure you get your funding for it.
So thank you very much, Robert. I see no more question here in the chat. Thank you very much for your very nice and interesting talk. And I hope to see you in person in a near future, and also to have your visit here in Brazil in one of the next conference that we will organize next year.
Thank you very much for having me. Same here. Thank you.
And so soon you are going to receive the announcement of next CASS talk. So I hope to see you all in the next one. So bye bye to you all and have a nice weekend.